In this chapter, 4.3, we're going to look at logarithmic functions. Our objectives in this chapter are convert between logarithmic and exponential forms, evaluate logarithmic expressions, apply basic properties of logarithms, graph logarithmic functions, and use logarithmic functions in applications. Definition of a logarithmic function. If x and b are positive real numbers such that b does not equal 1, then y equals log b of x is called a logarithmic function with base b, where y equals log b of x is equivalent to b of y equals x. In other words, the log of the base of the number is equal to the power, which is the same as the base of the power is equal to the number. This works both ways. Objective 1 is to convert logs to exponents. We will write each equation in exponential form. So in this particular case, we look at number 1 and we see that the base number is 4, the power is 2, and the number is 16. So immediately we can write 4 raised to the second power is equal to 16. This is in exponential form. We move to number 2. Again, the base number is 5 raised to the power of -1. So 5 raised to the -1 is equal to the number 0.2. So now we have number 3, which shows that log 8 of 1 is equal to 0. We can see that 8 raised to the 0 is equal to 1. Likewise, in number 4, the same thing is occurring. 23 raised to the 0 power is equal to 1. Now it's your turn. For each of the equations in the following, write it in exponential form. You will now pause and try your luck at doing each one of these particular equations. So here are our answers. A is 3 raised to the second power is equal to 9. B is 10 raised to the -3 power is 1 over 1,000. And C is 6 raised to the 0 power is 1. So now, in examples 5 through 7, we're going to write each equation in logarithmic form. So in the following, number 5, we have 2 raised to the 4th power is 16. We identify the base number as 2. Therefore, the following is true. The log of 2 of 16 is equal to 4. In number 6, the base number is 27. The power is 1/3. 3 is the number. So the log of base 27 of 3 is equal to 1/3. Finally, we have number 7. The base number is 1/4. The power is -2, and the number is 16. So this means that the log of 1/4 of 16 is equal to a negative 2. In practice skill 2, we would like you to write each equation in logarithmic form. You will pause the video and you will try your luck, and we'll come back and see what the answers are. So here was the answers that you should have gotten. 2 raised to the 5th power equals 32 is the same as log 2 of 32 equals 5. Number B, which is 10 raised to the 4th power is equal to 10,000, is equal to log 10 of 10,000 is equal to 4. In C, we have 1/8 raised to the negative 2 power is equal to 64. This is log of 1/8 of 64 is equal to a negative 2. Our second objective is to evaluate each log expression. In other words, evaluate each logarithmic expression. To do this, I rewrite the numbers based on the base number. So for example, I will rewrite log 12 is equal to 12 raised to the 2nd power. Well, when I see this, I immediately know when I evaluate this, it's just equal to 2. With number 9, we do the same thing. We say the log of 64 is equal to 64 raised to the 1/2 power, which is just 1/2. So for the log 3 of 27, I can write it in the following fashion: log 3 of 3 to the minus 3, and of course that's just equal to a minus 3. So when we evaluate it, we actually evaluate it based upon our rewriting of the number based on the base number. Now it's your turn to practice what we have just seen. Evaluate each expression. Please pause and try each of these expressions. So here are the results that you should have obtained. I rewrote A in the following way: log to the 5th of the number 5 raised to the 3rd power, which is just equal to the power of the number, which is 3. For B, I have log 3 of 3 raised to the 4th power, which is 81. And we can see that it's just the power, which is 4. The log 4 of 4 raised to the minus 3 power, which is 1 over 64, is just equal to a negative 3. So we have new ways to write certain types of base numbers. For example, the common and natural logarithmic functions. The common logarithmic function, which is y equals log 10 of x, is just written as y is equal to log x. The natural logarithmic function, which is y equals log base e of x, is just written as y is equal to an ln of x. Both of these numbers are in your on your calculator, and we will use them to evaluate logarithmic functions. Now we're going to evaluate the common log and also the natural log. So number 11 is evaluate the log of 100. So we know that this is base 10, so this is the log of 10 squared, which is just 2. Number 12, we have the log of 10 to the minus 4 power, which is just equal to minus 4. The natural log of negative 3, well, that's just equal to n minus 3. And the log of the natural log of e to the 10 is just equal to 10. Now it's your turn. You're going to evaluate the following expressions, both for the common log and for the natural log. So here are the answers that we have for each one of the expressions above. So for A, we rewrote it as log 10 raised to the 7th power, which is just equal to 7. B is log 10 raised to the minus 1 power, which is just equal to minus 1. C is log of e to the 5th power is just 5. And D is the natural log of e raised to the 1st power is just 1. So in many cases, we need to use our calculators in order to approximate a value for a logarithm. In this case, examples 15 through 18, we're going to use our calculators rounded to 4 decimal places. And we can also check using the exponential form. In other words, our example is the log of 43 is approximately equal to 1.6335. When we check, we put 10 raised to the 1.6335, which is approximately 43.0031. Luckily, your calculator actually has what's called an answer key down in your right-hand corner of your calculator. When you press that key, you typically will get the exact answer of when you do the anti-log. When I say anti-log, if this is the logarithm, then a log 43, the answer that I get in my calculator, I can just hit the 10 raised to the x power, and when I do that, I can hit the answer, the second answer on the TI 83 or 84 and get the exact number 43. So we're going to try using our calculators for 15 through 18. We will provide you with the answers. I would like you to pause temporarily and try to do this on your own, and then we'll come back with the answers. So here are our answers that we have. The log of 200 is approximately 2.3010. The log of 0.074 is a negative 1.031. the natural log of 200 is approximately 5.2983, and the natural log of 1.005 is 0.0050. So again, you can try your luck. You can use your calculator to do these particular problems, A through F, and we will show you the answers to these particular problems in just a few minutes. So in this particular problem, the log of 229 is 2.360, rounded to 4 decimal places. I've done something interesting here. I took the log of 3.76 and I added it to the log of 10 to the 12th. We will talk about that in the next chapter. It ends up being, when we take the log of that, it's 12.5752. The log of 0.0216 is a negative 1.666. The natural log of 87 is 4.4659. The natural log of 0.0032 is a negative 5.7446. And finally, the natural log of pi is 1.1447. Objective 3 is to apply some basic properties of logarithms. We will notice that the log b of 1 is equal to 0, primarily because you can see that b raised to the 0 power is just 1. And the log b of b is just equal to 1 because b raised to the first power is equal to b. And the log b of b to the x is just x because b to the x is equal to b to the x. And finally, the log log b of x is just equal to x because, as I say, the base of the power is just equal to the number, and in this case log b of x is just equal to log b of x. So in this example we're going to simplify each expression very, very quickly. When we take a look at it, we see the log base of 19 is just equal to 1 in this particular case. In number 20, log 10 is just equal to 1. The natural log of e is just equal to 1. The log of 273 of 1 is just equal to 0. The log of the base of 1/8 of 1 is just equal to 0. The log of 30 raised to the 10th power is just equal to 10. The natural log of e to the minus 12 is just equal to minus 12. The log of 10 raised to the log of 14 is just 14. And the log 8 raised to the log 8 of 5 is just equal to 5. So our objective 4 is to graph logarithmic functions. Example 28. So our function of interest is y is equal to log 3 of x. We're first going to rewrite it in exponential form. So in this case, we have the following. 3 to the y is equal to x. Now we did that on purpose because now we can evaluate for each value of x, we can evaluate a particular y. So for example, I will let x equal 1. If x is 1, y is 0. We can see that immediately through our exponential form. Now we're going to try if x is 3, we see that y is 1. If x is minus 1, right, actually that's not correct. If y is minus 1, we have 1/3, right? If x is 9, for example, we have y is equal to 2. And so those are our starting points in graphing our equation. So in this case, our vertical asymptote is going to be the y-axis because x cannot be 0, right, in this particular case. So we will put a vertical asymptote right here on the y-axis. Now, x can be 1, and so when we put 1 here, we see we're at 0. When x is 3, 1, 2, 3, we have x is 1. When x is 9, we have 2. Now we also have when x is 1/3, and of course if x is 1/3 it's down this way, it's at a minus 1. So this function is getting closer to 0 there, but now it's coming in this direction. So here's what our graph looks like for our logarithmic function. So now we're going to look at the following function. F of x is equal to log 4 of x, and we can rewrite this in the exponential form as 4 raised to the y power is equal to x, to get us a better feel for how to pick x. So when we pick x as 1, we get y is equal to 0. When x is 2, we get y is to be 1/2. When x is 4, we get y to be 1. When x is 8, we get 3/2. When x is 1/4, for example, we get y is to be minus 1. And if x is 1/2, we get y to be a negative 1/2. So now we will go ahead and graph our function. We know that at 1, we're here, and we have a horizontal asymptote. We can't cross the y-axis, so we have a horizontal asymptote there. Now we'll go ahead and put our points in. At 2, we're at 1/2. At 4, 1, 2, 3, 4, we're at 1. And at 8, 1, 2, 3, 4, 5, 6, 7, 8, we're at 1.5. And certainly at 1/4, we're at 1. So this thing is actually going like this. So there's our actual function, and that's how we graphed it. So we're graphing exponentials and logarithmic functions. They're inverses of each other, and you can see that the logarithm of y is equal to bx has the same capabilities as y is equal to log b of x. They're inverses, so you notice that the domain of one is now the range of the other. So for exponentials, the domain is a negative infinity to infinity, but the range is from 0 to infinity, and this now becomes the domain for our logarithmic functions. And then the range for the logarithmic functions is the domain of the exponential function. Notice that, again, our horizontal asymptote for the logarithms is y is equal to 0. For the vertical asymptote, x is equal to 0. So there's where you have the changeover from exponentials to logarithms. Finally, both points pass through 1, but for the exponentials they pass through 0, 1, and for the logarithms they pass through 1, 0. So in example 29, we're going to graph the log base 2 of 1 plus x plus 2. And we're going to look at it in terms of a transformation. Here we have f of x is equal to a log b of x minus h plus k. So for exponential functions, the horizontal asymptote is k. We will now see that in fact it is h that is the vertical asymptote for logarithmic functions. So in this particular case, for y equals log 2 of x plus, or 1 plus x plus 2, the vertical asymptote is at minus 1. So we're going to put in the vertical asymptote at minus 1. This is critical in terms of our understanding of how to graph logarithmic functions. Now, when we look at our table, and this is where we're going to just hit x and y, now when we look at this table, we will let x equal 0. When we have x is equal to 0, we have log 2 of 1. Well, log 2 of 1 is 0, plus 2 is 2. When we let x is equal to 1, we end up with 3, because log 2 of 1 plus 1 is just 1, plus 2 is 3. And then when we have 3, we have 4. So we're going to just plot these points. We know where the asymptote is, and we know the general form of the function. So when we look at this, we are going to plot the point at 0, 2. So at 0, we are at 2. At 1, we're at 3. At 3, 1, 2, 3, we're at 4. And so this function looks approximately like this. So again, we're going to graph our function. We know where our vertical asymptote is because the way we would go about this is x minus 4 has got to be greater than 0. So x has got to be greater than 4. So this is our vertical asymptote. And so at 4, we will put in our vertical asymptote here. And so now our function will go to the right of this. So we'll now look at our table, x and y. So assuming that x is 5, we have log 3 of 1 plus 1, so this is at 1. The next one that we're going to hit is going to be 7. When we hit 7, that's log 3 of 3, which is now 2. So we can place these points and kind of get a feel for how this thing works. We're at 5, 1. We're at 7, 2. So our graph looks something like this. Actually, it's probably closer to that. But here's what our graph looks like. So here we're just going to give the domain and range in interval notation. Determine the vertical asymptote. Well, that's simple. X plus 3 has got to be greater than 0. So x has got to be greater than a minus 3. This tells me this is the vertical asymptote at negative 3. So you can see at negative 3, 1, 2, 3 is our vertical asymptote, right? And so here is the domain. Our domain is at negative 3 comma infinity, and the range is negative infinity to infinity. Example 31, we have y is equal to a negative 2 log 2 of x. We know that x in this case has got to be greater than 0, right? So there is our horizontal vertical asymptote, and we see that it's that way, right? And so our domain is simple. The domain is going from 0 to infinity, and the range is all real numbers. So it's your turn. You would want to pause this and write the domain in interval notation for the following two expressions of logarithms. So pause your video and try your luck. So here are the answers to skill practice 9. For A, our domain is a negative infinity to 1/3, and you can see how this was solved. we let 1 minus 3x is greater than 0. So negative 3x is greater than a negative 1. So x is less than 1/3. So that means our domain is a negative infinity to 1/3. In part B, again we let 2 plus x is greater than 0. X is greater than a negative 2, which implies that our domain is negative 2 to 0, to infinity. So our final problem or objective is to apply logs to application. So the absolute magnitude m of a star is the apparent magnitude of m a star would have if it were placed 10 parsecs from Earth. The lower value of the magnitude, the brighter the star. Our Sun has an apparent magnitude of a negative 26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of a negative 1.44. The Sun appears so bright because it's very close astronomically speaking. The formula is the following. The absolute magnitude is equal to the apparent magnitude minus 5 log parentheses d divided by 10. D is the distance. So it says a star's absolute magnitude and apparent magnitude and its distance d from parsecs, Earth's parsecs. Now, given that if Sirius is 2.637 parsecs from Earth and the Sun is 4.887 times 10 to the negative 10th parsecs from Earth, what is the absolute magnitude of each star? So now we're going to do our calculations. So here is the answers. We have for Sirius, m is equal to a negative 1.44 minus 5 log of 2.637 divided by 10, which is equal to 1.4544. And the Sun, which is m equals a negative 26.76 minus 5 log of 4.887 times 10 to the negative 6 divided by 10 is equal to 4.7948. So based on the absolute magnitude, Sirius, since it is a lower number, is essentially a brighter star than our current Sun. Well, that concludes our chapter 4.3 on logarithms. Please work the problem sets of the day and look at your homework assignment and exam. And we will be discussing more issues on logarithms in chapter 4.4.